today. Really excited to have everyone here. My name is Era. I'm the co-founder for Edge. Super excited to work with Arize AI, Weaviate, Cohere, and the broader DSPy community to talk about this framework today. So to get started, I want to give a bit like background about this space, about us, and our approach here. So I'm the co-founder for Edge. Me and Ilya Poloskin, one of the co-author for Transformer paper, we started Edge about 2 years ago, focusing a lot on Edge model and the open source tech. And with our community here, each month we host a lot of different workshops, summit, like to dedicate a lot of the open source AI acceleration and education here. And our ecosystem partner, amazingly, in the past year, we have been working with a lot of great large model issuers, a lot of enterprise AI partners as well, and look forward to partner with more people since today as well to accelerate this adoption. And our core thesis span across 4 major areas. Number one, we really focus on open source acceleration. From the Transformer paper, it takes about 6 years to really, from paper implementation to application. We really want to supercharge for that part. Second, we also focus a lot on story intelligence stack, focus on user AI, user-owned AI future. Third, edge computing robotics. I know the past week has been a lot on XAI conversation on that part. We're also very excited to look at how different agents can install on different edge model as well. Lastly, collective governance. How to think about alignment, how to govern this AI future. We want to be the partner on work on that part as well. So we really want to highlight today, first of all, we really want to thank to our major enterprise partner, Digital Garage, which is the major whole sponsor for this entire venue. They're one of the top, I would say, Japanese conglomerate, and they're looking forward to working a lot of emerging AI startup to really accelerate this future. So if you're interested to multi-linguistic model or think about different enterprise AI, find us here. We would love to talk to you here. And hopefully in this summer, we're going to launch our open source campus. It will become basically an open source accelerator in the co-working space. So if you're an open source guy, want to get a bit acceleration, get a working space, talk to me afterwards. We're going to give out both across our open source grants and a lot of our mentorship network across our open source network here as well. So yeah, so we're gonna do a lot basically Open Source Friday and also a lot of upcoming summit as well. So if you're interested to partner with us and talk more about Open Source Campus, find us after. So thank you everyone, and I will pass the mic to our major host today.
Hey everyone, thanks so much for coming out tonight. Really excited for the content that we have in store for you all. Just wanted to make a couple housekeeping notes for everyone. We are going to be recording this session, and we will email out the recording to everyone after the event. We'd also like for you to hold your questions until after each of the presentations that we go through today. And lastly, we do have a few flyers around the room with QR codes where you can access each of the platforms that we're going to be talking about today if you'd like to check them out for yourself. Hand it over to Erica here. She's going to give us an overview of the different platforms we're talking about today.
Thanks, Sarah. Yeah, thanks everyone for joining. This is very impressive. I'm from Boston, so I'm not used to these kind of events, but I'm very thankful that all of you are here today. For those of you who maybe aren't familiar with DSPy, Weaviate, Arize, Cohere, I just wanted to provide a quick overview, but I'm not one of the official speakers, so they will go more in depth. But basically, we have Cohere, and they offer embeddings, embedding models, language models, and re-ranker models, and then it connects to the Weaviate database, vector database. And then we have a layer on top of that as DSPy for the orchestration, and then we have the monitoring and observability to see your DSPy program and kind of find the tweaks on maybe where something is going wrong or maybe how you can improve your application. So that's just a quick overview of what it is. We're actually starting with Cohere. So we have Daniel Simig here, and he's going to be giving us an overview. So if you can give him a round of applause, let's get him on.
All right, does this work?
It's working.
Can you hear me? Ooh, okay. Hello, everyone. My name is Daniel. I work at Cohere, and I'm trying to put this presentation on full screen. Fantastic. Right, so I think most of today's talk is going to be about optimizing pipelines and all of these things. So I thought I would spend the first couple of minutes of this workshop to talk about the building blocks that we might want to use for these pipelines. I work at Cohere, so we are pretty good at building these building blocks, so I thought I would share you some of these blocks. Very briefly, I'm just going to give you a quick introduction of what Cohere is and what we do. And I'm going to spend a little time on Command R+, which is our latest generative model. But I personally work on the search space, so I would prefer to talk more about the search side of things. Yes, I was very lazy, and I just kind of copy-pasted the first good-sounding sentence from our webpage here. But what does that actually mean, that we are the leading enterprise for AI platform? When at Cohere we work with enterprise, we have all kind of data coming in, very weird formats and shapes, the different interfaces, services that you have to interact with. So it's kind of a messy business. But still, we must be very, very consistent in not doing any kind of hallucination. We really have to be good at grounding all of the things that we generate in some kind of knowledge that enterprise have. We also have use cases from many, many different languages. So you can't just kind of stick with English and just not care about other languages. And most importantly, maybe, you cannot just go crazy and spend a lot of money on the biggest models ever. You have to be providing a very good trade-off between price and performance. So that's kind of going to be the theme for most of this talk. So you're going to see these things come back once in a while. So I guess when React started, it was fairly simple. You would just take your documents, you would chunk them up in some chunks, put them into some database. For each of them, you will have a vector. You will try to hope that whatever vector search you're doing is going to find some important part of your documents. Hopefully, you can fit it into context. Your language model is hopefully going to find the most important information, and you hope that things will just work out. When you do things for real big companies, and I need to make this thing disappear from there. Okay, that's gonna work. No, thank you. Okay. Right. So when you work with real enterprise, you'll have a lot more complex scenario. So maybe your language model needs to route different kind of calls to different search systems. Maybe it has to use tools. Maybe it has to rewrite your query. Maybe it has to do multiple steps of maybe a search and some kind of tool use. And even within search, it has to interact with a lot of different systems, maybe a database, maybe emails, maybe some PDFs. So we are looking at a lot more complex scenario here, and to that we have different solutions at Cohere. Right. So today I'm going to be talking about two of these parts. One is the generative model that is able to actually interface with these things. And the other part is search. How do you make search work better for enterprise data? Well, I don't work actually on generative models. I'm going to keep this short, but we have a new model, Command R+, that I highly recommend you could try out. It is built for business, as we call it. What does that mean? It's very good for RAG. We have, big context length. It's very good at citations. It's going to kind of tell you why it's answering what it is answering to you. It is able to do multi-step tool use. It can combine different steps. It can rewrite your queries. All of the things that I talked before. It is priced at a point where it's a very good trade-off between being able to do those things and not costing too much. Again, you will see these in the upcoming slides. And we have some multilingual capabilities. And technically, the models are available on Hugging Face. It's a bit big, and also it's non-commercial license. But you're still free to play around with it if you feel like. Just to demonstrate a couple of these things, illustrative examples. It's quite cheap compared to something like GPT-4, but it is quite on par with GPT-4 on a lot of tool use and QA type of tasks. Also, a pretty cool thing that I think is nowadays underappreciated is that it's quite good at multilingual. Again, a lot of people are asking for that. And I'm going to wrap it up here with generative, and I would prefer to talk more about the search side of things. because I think there's a lot of interesting things happening there as well. Again, previously, things that you would do would involve using single dense embeddings and doing some sort of dense vector search and hoping that things work out. That's great. You have a lot of models on the market. I guess plug, we have our own embed v3 at Cohere. Come try it out. It's pretty cheap. You can quantize them even cheaper. Again, try out Cohere. And for some use cases it works. But then when you try to make these things very reliable for actual enterprise applications, maybe you will hit some issues. First, people like to talk about context length. Great, I can scale the context length of whatever comes into my embedding model, but honestly, you're still kind of stuck with a single embedding that has to interact in a vector search way, and it might not work out very well. So for example, if you have products that have like shape, color, different types, all kind of complex information, it's very hard to compress all of that into a single vector space. And yes, the other thing is when you have something like an email with some attachments and some people saying things and maybe some replies and all of that, it's fairly complex data. It's not very realistic that we can all chunk it up into equal size chunks and represent them as just these kind of atomic units of things. So maybe this is also something we have to think about. So a couple of interesting things that are happening in the embedding world. Well, first you can have multiple embeddings. You can have Colbert. Yes, Omar is here. I think he knows these things more than I do. So if you have any questions about Colbert and multi-vector stuff, we have a person here to talk to. But maybe something that is a lot easier to use is something like re-rank, which means that you can just kind of slap one more extra call to your code, or maybe if you're working with Weaviate, you can just configure one extra little step, and that's actually going to add a lot more intelligence to your search systems. Finally, we are working on something cool at Cohere that I sort of want to save 1 minute at the end. You will see very soon. So quickly, re-rank. What does re-rank do? You can do your normal story. Query, you can look things up. You will get some documents. Maybe some of them are good, some of them are not. But now the cool thing you can do is that you can take re-rank and use a cross-encoder that kind of understands both the query and the document at the same time, and actually gets you a lot more precise results in pretty much one line of code. So I illustrated here as reading out that 0.1 score thing from the top of your results. It literally is as simple as this, or if you're maybe in Weaviate, then you can probably configure it in some way. And it does, give you pretty significant improvements. So if you have not tried re-rank, I would urge you to try. We have our latest re-rank v3, pretty good at code, multilingual, kind of semi-structured data when exactly you have these more complex data points that have, maybe, again, color, shape, whatever, numbers, so on and so on. And I think this is going to be my last slide, and maybe kind of the most vague and open-ended slide. We are working on something that would approach the search problem in the kind of complex data space in a lot more, I want to say, holistic way. Two key things that I can talk about, because there are some other things that I cannot talk about, is that maybe the idea that we just want to chunk everything into sort of independent chunk and retrieve over them is not the best idea. So what if I sort of, instead of like having this email and attachment combination chunked up separately and being retrieved, what if I just have one fairly complex representation that captures all of these things? And then, sure, now it's a much harder challenge to model this because it's not so nicely chunked up. But maybe you can build some models that are actually able to understand all of these different relations and kind of get out the information that you need from these and retrieve from your vector database. And yes, this is hard. You can't prepare for all possible data that will come in. It's kind of hard to make it work with standard databases. And there is literally no evaluation data other than actual clients that you work with. So it might take some time. We have a very small private beta for this. But I think, something in the next couple of months, maybe that kind of time, we'll have something public that you can try out. And I think that's it from me. Thanks very much. And one more quick thing. If you have never tried Cohere and you want to try Cohere models for today's workshop, we have like a little $10 extra code that you can take, and yeah, just try Cohere for $10 credit and mess around with DSPy or whatever you want to. Thanks.
Awesome. So first of all, before I even dive into it, it means everything to me to see everyone here. And DSPy has just been one of the most fun technologies I've ever gotten to work with. And to be up here with our collaborators at Cohere, Arize, and have Omar here, it's awesome. All right, super cool. So this is going to be a pretty raw look into our first efforts of building a product around DSPy and how we're trying to integrate it with the services offered from Weaviate. So we've obviously seen a ton of opportunity around RAG, and we characterize RAG to be a simple AI system where we just read from the database to then pass in the results to generate with the language model. But now with DSPy, we're embracing this compound AI systems where we have several calls to LLMs, multiple tools, say search indexes, calculators, Python code executors, and we orchestrate all of this in really interesting ways. So one of the such categories of tool use that we're really excited about is not only reading from the database in RAG, but also writing to the database. And this is something that we call generative feedback loops. So one of the best examples we've seen of generative feedback loops has been Shopify's Magic, where you take a product and you generate alternate views of it, like what this CD player would look like on a bookshelf, as well as write descriptions. And so they're using generative models to then enhance the descriptions of their products to better sell them and just overall create more information from their raw data. So in this talk, we're going to look at a case study with the Weaviate blog post. It's like chat with documentation. This is maybe the most common sort of use case we're seeing with RAG and all this kind of compound AI system stuff. So underneath our Weaviate blog post are these markdown files. So markdown files are, our DocuSource is able to render these into beautiful web pages, but we load these in the database, and all we have is this string, this content, there's just this markdown file, right? And for the sake of this, let's also pretend that we have a database table with friends, where we have the name of the friend, a biography, and maybe some recent works. So the first thing we do is we turn chicken shit into chicken salad, and this is something that Bob wanted to emphasize when I was talking to him. He loves this chicken shit to chicken salad. We have our markdown, and we use the LLMs to convert it into structured data. So we have all the common ways of structured data. We get the title, we get the author, we get the date published, all this kind of common sense stuff that you can maybe even just do with regular expressions. But now we also can, write a summary or summarize the topics that are covered in the podcast. The blog post. And then we also can write personalized summaries. So say we have our friends and we have this, our database that we have Omar, Mikyo, Sarah, and Daniel, and Omar animated in there, but so we take one of our blog posts and we have our biography of Omar and we say, why might Omar like this blog post? So we're writing back into the database and creating new value. Now we have personalized summaries, a personal reason why you would care about our new software release or whatever it is. So starting from just the content string and the name of our friends and so on, we're able to generate all this structured data that we can query more efficiently, navigate our database sources, and all this kind of stuff. So in this talk, I want to present where we're at on integrating this as a service that you can quickly just hook up into Weaviate, whether that be running it with Docker or we're moving into this kind of service layer thing. So the first thing we've done is abstract DSPy a bit further as well. So we now have a more generic task description where we have your task is to generate the value of a property by following the instruction using the provided name, value, property references. And then we just interface the actual kind of instruction via the instruction as an input field and the property value where you tell us, say, author, email, things like this. So first, let's take a look at the generality of this. So if you're extracting the title, you just say analyze blog post, extract as title, on property is title. You can then do that for author. You can do that for the date published. You can also do that for writing the summary. So similarly, when we're trying to write the personalized summary, we can easily template in this instruction. And now we have this generic kind of single layer program of how we're going to interface updating these properties with one DSPy signature. So quickly, let's look at a demo. Okay, so in this demo, first you see how you connect to Cohere's command R+. You can set the max input token. So in this case, I think one of the most underrated aspects of transit, well, long context, I don't even say that's underrated, but so we're setting 32,000 inputs that we can give to our model, and then we're going to constrain the output to only 4,000. So you can always just kind of check the connection with your language models by just running it quickly. So the first thing we do is we connect to the Weaviate client, we upload our blog post, and again, all we have so far is just these markdowns. So we're just uploading these raw markdown files into our database. Oh, sorry. And now we're running our update. And then we just have our update property program, a quick demonstration again of the generality of it and of personalization. And so now we connect to Arize Phoenix. Okay, so in a second, hopefully you'll see the value. Okay, so here's the, okay, so I'm gonna run this quickly and then we'll see. So what this is doing is it's looping through the blog post and it's extracting the author as given by just passing it into our DSPy program. But our plan is to replace this and put this into our Python client where you would select the collection and you have .data, .generative feedback loop, and then just .update property. And this would be how you would access this functionality in Weaviate. So as you observe as this is running and it's updating our properties, we need some way of, how is this going and monitoring it. So that's where we use Phoenix. And Phoenix is catching all these calls as we're logging it, as we're running the updating of our properties. We see things like the latency, the tokens used, and there's all sorts of exciting things with interfacing metrics, and we're super excited about partnering with Arize Phoenix and Arize, I think Phoenix is the open source, but Arize to build out this kind of logging for this generative feedback loop. So as mentioned, our plan is we open source this service and you can use it with, it's open source on Docker, so you can add it to your services. You have, say, Weaviate running as well as generative feedback loop, and then you have the LLM with, say, Olama. So more closely what this looks like, and sorry, I got a little lazy with animating this in, but the first thing you do, so when you're designing these microservices, you want to have, not too much coupling with how you send the request to each of the services. So the first thing we do is we get the objects from Weaviate, and then our client receives the objects back. It parses them, and then it sends it to the generative feedback loop with this one update property endpoint because we've abstracted it, so we just have this one program and this one update property. Then we send it to the LLM that would also be Dockerized, and then we also have Arize running in Docker, so this would be one way of orchestrating this kind of system. So there's some other little details that are in here. Okay, so the next thing that I'm maybe talking to maybe people who are more into DSPy is can you achieve this all with one call to the large language model? Extracting the title, extracting the author, writing the summary, you can just do this in one call to the LLM. You don't need to break it into multiple calls. But it's not super clear yet to us how to interface this. Because if you remember, we originally just have this property value, it's a string, and say our chicken salad, what we want, we would want to type something like this, or saying all the stuff that we expect back for it. But what we need is a way to synthesize this on the fly. And so I don't have a good answer for this yet. These are just some notes of thinking about this, synthesizing type assertions. I highly recommend this paper, Spade, from Shreya Shankar et al. And it's a really interesting way of how you can give it this dynamic instruction, synthesize assertions. So next up, let's talk about the DSPy optimizer. So DSPy optimizers are maybe the most Wild West thing about DSPy. And the way that we see it is there's three general categories of this. There's in-context learning, where you're putting task examples in the prompt. There's prompt tuning, where you're tweaking the task description. And then we see those two as being pretty related. You're trying to better prompt the model, whereas gradient descent we see as a pretty different paradigm, and we haven't even really started working with that yet at Weaviate. So I thought this was pretty funny, this blog post, especially the title, F you, show me the prompt. So this is a look at how DSPy renders these prompts. So you start off with the task description. This is where you're saying your task is to generate the value of product, blah, blah, blah. Then you have the input-output field, and then you have the current inference, and then here you would put task examples, but I omitted it here. So I think the most interesting thing for people to know is this DSPy MIPRO optimizer. So the MIPRO optimizer, it's kind of the heavyweight, most cutting-edge way of doing this, where the first thing it does is it's going to loop through your data set and summarize it to observe what is your data set about? Because this is going to help tremendously when it's trying to paraphrase the instructions or produce examples to have this kind of global summary of what the data set is talking about. So I'll skip walking through this, but it evaluates the metric, and then maybe most interestingly is how for each of these candidate instructions, it's also going to generate a candidate example to put in the prompt, and that gives you a better sense. By combining these in-context learning examples with paraphrasings of the task, you overall get a better sense of the performance of it. So another thing that we're really excited about is working on our partnership with Weights and Biases for monitoring this kind of optimization. So here's just a quick example of what that looks like, in the final prompt that it produces, and then how you would update your task description with this prompt optimized by MIPRO. So some of the benefits of, is that my 10 minutes? Okay, I'll go through it quickly. Okay, so so the benefits of DSPy optimization, performance, cost, and speed, switching to new LLMs, and we think this is just the most Wild West aspect is this kind of, okay, so really quickly, I just want to end with this. So we turned chicken chit to chicken salad by just kind of structuring the data, but now we want to say this is like chicken salad to filet mignon and lobster, which is about, you have your blogs, you generate unanswered questions. Like how many of us, you write something and you ask Cloud, like how is this? Is it a good writing? What are some questions that aren't answered? And from there, we're looking at systems like Storm, and we have a system called Hurricane that's inspired by that, where we're trying to generate new blog posts to answer these questions, feed that back into your database. And not only are you structuring it, creating the chicken salad, but you're also creating new value by creating these unanswered questions and using the tools, these Python runtimes, all this kind of stuff to generate new information to feed in the database and create this kind of, AI creating new information for us. So with that, I'll just skip ahead a lot, but, again, so we're thinking about how we containerize this, and how you do streaming is a pretty interesting question. Anyway, so that's my talk on generative feedback loop DSPy. This is our service layer we're building with DSPy around the database to structure our data and create value. If you want to keep up with us, we have this DSPy integration page, and again, we're just so lucky to be working on this technology. It's super cool.
Better one? Okay.
Thanks.
All right. So today I'm going to be talking a little bit about observability with DSPy. So, kind of with the advent of LLMs, we've moved from kind of a deterministic system, right, with things like compilers to give you some sort of determinism, to kind of this much more probabilistic system, next token prediction. And so to kind of reconcile for this change, we've had to kind of change our programming models, right? And we're really excited about things like DSPy that kind of change the way we program with these systems. I really love the word that Omar uses, like trying to build the application, artificial programmable interface. And with that shift, we need kind of observability to shift as well. And so at Arize, we build tools that observe these kind of probabilistic black box systems and kind of give you tools to evaluate and reason about their outputs, to kind of get more deterministic outputs and improve and iterate on them. So today I'm going to tell you a little bit about Phoenix. So Phoenix is our open source offering, fully open source. I get to work on this day in, day out. It's really nice. It's fully private. It's fully compatible with kind of open telemetry, which is kind of the industry standard here with DevOps, but now we're moving that into the generative space. It's built with built-in evaluations for the specific task that you're trying to accomplish. And as you kind of saw with Connor, it actually runs anywhere. So it runs natively in a Jupyter notebook, a Colab notebook, a Docker container. If you're deploying your DSPy application to Kubernetes, it comes with you everywhere you go. So the one thing that the Phoenix offers is this generative AI debugger. So it gives you visibility into the application pipeline, specifically the DSPy pipeline, the modules that you build, gives you visibility into retrieval, latency, token counts, prompt templates, variables, and much more. It also is kind of the way through which you benchmark your generative application, right? So not only evaluating the LLM outputs, but also specifically like with Weaviate, you want to make sure like what is coming out of your vector store is properly appropriate for what you're trying to build. Being able to build custom task evaluations, these could be DSPy programs as well. And then you can send these systems, these annotations back to the platform and monitor them over time. So what does that look like in practice? So right now I actually have running kind of Arize Phoenix running as a container, and then we have a fast API application just sending traces over to that running application locally. And I have a fast API, Cohere, and Weaviate running full stack application. And what's really cool about it is it's like a very simple one-liner, right? So if you don't want traces, you can turn this off, and when you want traces, you can turn this on. But basically, you make no application changes to your DSPy program. You just kind of a few lines of code, and you're off to the races. So with that, I'm going to have to type, so I'm going to try to do this. So now you can see I have like a full stack application here, right? And so I'm going to ask a question like, who is Paul Graham? And sure enough, I get an answer out of this system with using Command R+. And it's kind of transparent to you that this is using DSPy, but let's go over to Phoenix. And now you can kind of see the input and output, but not only that, you can look at the latency, and you can kind of see from the outside how this program is constructed, right? So this is using the DSPy module. It's doing a forward pass to a retriever. So this is doing Weaviate. It's pulling out multiple document chunks. Then we're leveraging, chain of thought to do a forward pass to Cohere. And then, like the amazing thing that is about DSPy, it's actually constructing a prompt under the hood that kind of is taking that RAG and telling it to do some instruction following. So let's do something a little bit more fun. So let's take advantage of the DSPy compiler. So I'm going to do bootstrap few shot here. So I'm going to drag a few examples in here. I'm going to compile a new prompt. It's going to take a few seconds. And now let's ask some questions. So we say, what is Paul Graham's net worth? Behavior is very similar, but now if we come back to the system again, now we come into here, and then now if we actually look at the the retrieval call calling Command R nightly, you can actually see those like few shot examples kind of bootstrapped into it, right? So it's a really great way to kind of iterate both in your notebook and locally, and it gives you kind of visibility into the parts of DSPy that you might have not known about. Okay, so let's take this even further. So let's say you've optimized this and built it out end to end, and then you deploy it into production, right? Like, how are you going to observe that system? Is it doing the right thing? So the cool thing about Phoenix is like it has a robust API as well that you can pull data out of. And what we've done is kind of created kind of Python data frame, pandas native kind of data science tool on that side as well. So now we can just connect to that running Phoenix instance, pull out basically data sets that you can run evaluations over. So now we can get kind of the question, answer, and reference that's coming out of DSPy. We can also evaluate retrieval. So we're going to pull out the documents and the chunks and the questions that were used to do the queries with Weaviate. And then we're going to perform retrieval evaluation. So we're doing like the relevance evaluation, like how related is it? And we do automatic like information retrieval metrics, right? Like NDCG, precision, hit rate, things like that, things that you really want to care about when you're optimizing your retrieval model. We also can do kind of response level evaluations, like how well is the LLM following instructions? Is it answering questions about how your application is running? And you can all do this with production data as it's coming, kind of feed it back, creating feedback loops into your system. And then the cool thing is you can kind of now log this back to your running Phoenix instance. And now when you come back, you can kind of see everything's been labeled with the evaluations. You can kind of see how we've also done kind of the retrieval metrics, so how well is Weaviate answering your questions. In this case, this is a really good example, right? So we have NDCG of 0, relative precision of 0, false hit rate, and that's kind of causing an incorrect response by your LLM. And so you can kind of go into those retrievals and see that, because we never chunked anything to do with Paul Graham's essay related to his net worth, it's actually, completely putting irrelevant context into your LLM, causing it to hallucinate and produce bad responses. So that's Phoenix in a nutshell. It's open source. built-in DSPy. I like Connor calling it, it's like kind of DSPy ops, if you will. Free to use. That example is fully on GitHub, so trace, evaluate, and iterate, and come talk to me later.
All right, thanks everyone for joining us today. It's awesome to see you all. So, I thought today I could just sort of discuss the past, the present, and the future of DSPy. Lots of sort of big ideas. We'll look at some code, but try to cover sort of as much as possible of the foundations of this stuff and why we do all this, where people should focus, etc. And the context of a lot of what I talk about is that it's never been easier to prototype impressive AI demos. And this is something that excites all of us, that you can just sort of go to this website called ChatGPT, can ask it questions, and it's not only going to find documents that answer your question, it's actually going to synthesize stuff. All right. So, it will generate answers just for your question. So this is an example of me asking it to help with a task, asking it to parallelize a Python loop for me. And it absolutely did. So at this point, we're all familiar with the problem with these language models, which is exactly their strength. They are so fluent that when they make mistakes, they can be really hard to detect. Stanford was not founded in 1891, although that's close, which makes it misleading. And the whole reason I asked it for help with this code was that I knew there was a dependency between the iterations of my loop. So when it just gave me back code that didn't fix that, code that had data race, I was not impressed, and I was glad I didn't rely on that output. So the big picture here is that we can build impressive demos really quickly that look pretty decent at first, but turning those into reliable systems that we can put in front of users, systems that are cost-effective, that are worth scaling, is still a very hard problem. And this is exactly what all of this stuff is trying to help with. And I've given this talk before a lot, and only recently did someone tell me, by the way, there was another mistake in the answer, and I hadn't noticed it myself, even though I'm just telling you about how these things make mistakes. Stanford was not named after Leland Stanford; it was actually named after his child, and so that's yet another mistake, and it's in a very, very popular head entity, so that's actually striking. And this stuff has a lot of implications when you put stuff in production, or you rely on it as a user, or when your users rely on it. Now, I'm not saying ChatGPT sucks or language models suck or whatever it is because they made a couple of mistakes. Every AI system and everything we'll build with DSPy and everything we'll talk about today will make mistakes. The problem, though, is the monolithic nature of language models, the way in which they are indivisible and black box and opaque. And that makes it really hard to control them when we're building systems, to debug them when they make mistakes, as they often do, and to improve our systems that we build with them when we sort of see avenues for doing that. And one argument I like to make all the time is that we do know how to build controllable systems and how to improve them in a modular way, and that's just called programming. So I'll talk today about this notion of language model programming. Or basically using language models to build and to optimize, which is important, modular programs that can be more accurate, more transparent, and even more efficient than using the best language models in isolation. And so what does this look like in practice? Ultimately, a lot of the stuff that we do with these language models is some kind of information system. Basically question answering is a large blanket under which many things fall. Obviously, we do a lot of things that are not really quite question answering, but sort of the general paradigm that we're looking at as a default right now in NLP, and it's shifting away from that, is that you have this amazingly powerful feat of engineering that's a monolithic language model. You give it your questions, you give it your prompts. Got to be careful how you prompt, but eventually you give it some string, and it gives you back some text. And it's just this one indivisible function that is doing this stuff. And so what we've seen over the last few years is the kind of things that we were doing in research and sort of were not really as mainstream as they are now yet, like retrieval-based NLP, or as people call it nowadays, RAG, is really this notion that we can break down problems and go to our language model and actually use it to play smaller roles in a bigger program. So now it's actually playing a modular role. And so in a simple RAG application, as folks have already discussed, we're not giving our question to the language model directly. We actually sort of have this intermediate retrieval step, which is played by another transformer. It will consult the text corpus, surface some of the top results, and then these results are going to be sort of leveraged to do a much easier task, right? We're not trying to ask our language model to know everything. It's just going to use these sources to answer questions. And so essentially what we're doing when we do something like this is that we're decomposing what seems like a really hard problem, which is know everything about the world factually and know how to attribute it to sources, which is very difficult, to a problem of just know how to find stuff as a search model, which is something we know how to do, and know how to use that stuff to answer questions. So why are people excited about this RAG stuff? There's a lot of reasons, but I think, in general, these types of decompositions offer us a few things. The first is transparency, right? You can look at the system, and maybe it said something right, maybe it said the wrong thing. Either way, you could go and peek into the system and actually find the actual documents that were sort of utilized by the different modules to say whatever it says. And that's great when it's right, because you can back up what you're saying. You don't just have to say, I'm trusting the system. You can say, well, here's why what I'm telling you is true. And you essentially remove the system as an intermediate element between you and other people you're talking to. But also when it's wrong, you can kind of start debugging and understanding what's going on with your system. And maybe it actually helps you revisit sort of some of your assumptions. The other thing that's awesome is updates, right? So if you have a language model, a lot of us don't train our language models from scratch, or just in general, you're not going to be able to get the best performance anywhere if you're not the team training, some of these foundation models, even if you're at the same companies. And in practice, we still haven't figured out, and let me tell you, we will never figure out a standard way for the standard type of autoregressive language model that we have now to update them on the fly with the same reliability that we have with, the stuff that they saw at pre-training earlier. And so what's really cool here is that with frozen components that just know how to play these modular roles, you plug in some extra documents in your text corpus, ta-da, your system knows extra information and can leverage it in various applications. The other thing that's awesome here is that because we've broken down this complex problem into multiple pieces, we can have a lot more efficient modules playing these roles, because the system does not need to remember everything. It does not need to sort of know how to cite its sources sort of off the top of its memory, which in this case is in the parameters. Instead, it could just play these more modular roles. Now, where all this stuff starts to sort of be more challenged is cases where, the problem decomposition is not so obvious. And it's not hard to come across problems like this. Complex question answering is one of these examples. So, if you're doing RAG, ultimately you're relying on what? You're relying on your retrieval model being able to find the documents that will help us answer these questions. Oftentimes, people are in the context of applications where they're writing whole articles or they're researching complex topics, and there is no document that covers every possible combination of interesting things you're asking about. And so this is, a place where language models ostensibly will shine because they're synthesizing everything in their parameters. They don't have a notion of a document anyway. They're able to make all these really good connections in their weights. And so, you'd expect them to shine the farther and farther along you go from a single information from a single document. And so this is an interesting place to start thinking about what modularity and decomposition would look like, because that's really where the action is. So this is me asking a simple question that's meant to be compositional. How many floors or stories are in the castle that David Gregory inherited? And ChatGPT tells me, and David Gregory is kind of a Scottish guy. He has a Wikipedia page. He's popular enough for the model to have heard of him. And it says that he inherited this Bamberg castle, which is a castle located somewhere, and it kind of is challenging to specify the exact number of stories in that castle because it doesn't remember. But then you open a new window and you ask it again, and it's like David Gregory is a fictional character. So without more context about the universe he's from, that's an interesting choice of words, it's challenging to provide a precise answer. So one awesome thing is GPT-4 in both cases kind of avoids making up a number for the stories. That's actually good. It wasn't as good like, if you tried it a few months ago. But no, I don't know what Bamberg Castle is, and he's certainly not a fictional guy. Well, actually, there's many David Gregorys on Wikipedia. This guy is a physician, but there are many others. And so this is wrong. So we say, okay, the language model knows David Grigory, and it actually knows the castle. It just cannot really connect the two because it never really was trained on enough data that shows both of these so it can extrapolate to them. And that's a recurring problem with language models is that, they're really good at so many things, and you can train them on more data to make them know more things. But whatever it is that you've taught them, compositions of that maximum set is something that they really struggle with. And it's a very fundamental limitation of the way they work as things that we train with gradient descent the way we do. So you might turn to RAG, turn to retrieval augmented generation and say, well, this will fix my problem. This will solve my problem. So you go and you basically take this question, and as we said, you give it to your favorite retrieval model, maybe Cohere v2, and you say, well, I have an index that has all of Wikipedia, which does talk about this guy, and in fact, it has enough information to answer this question. And so we find that it takes this thing, and the top result is about San Gregory Hotel. And San Gregory Hotel, you give this document to the language model, and it says it has 9 stories. This is a factual statement. It's directly taken from here. The model did not make things up. I'd argue it's not hallucinating. But the problem is this stuff is irrelevant. Nobody's asking about San Gregory Hotel. And you might look at this and be like, that retrieval model sucks. And I can tell you it does not. But the reason it does not is that there is no document in this data set that talks about San Gregory, David Grigory's castle number of floors. There isn't. And so, it's a retrieval model. It'll find the next best thing. And the next best thing is number of floors and something that has the word Grigory. It's actually kind of nice. All right, so I guess we don't need are we going to need the results later? I guess we don't. But yeah, point is, I'm not sure if we'll need this later or not, but there's a nice kind of benchmark called hover where documents need to reason across, up to 4 documents from all of Wikipedia that the system needs to find. And if you just do like direct retrieval, top 100 with a retrieval model, you only find all the relevant documents for that query in the top 100, 45% of the time. And so that's more than half of the cases where your top 100 results are missing the relevant documents. So this is where a lot of sort of the, forms of more interesting composition happens. And this is kind of like the next simplest thing is multi-hop retrieval. Basically, we can take the same question that we're working with and, now we're not trying to ask a model to answer the question, but we're also not giving it to a retrieval model, which is kind of a simple tool. It's not too smart. We're actually going to the language model and we're saying, could you help me break this down into atomic pieces that, I'll have a much higher odds at actually finding something that talks about it. And that's not obvious, right? How do you go to a model and actually just teach it that concept? That's actually very fuzzy to us, because I'm not really sure what I would do if I'm trying to decompose this and give somebody an instruction. Even if they're actually very smart and they can follow instructions, it's not clear how to do that. But let's say that we succeed, and we go to a language model and we convince it to reliably ask, well, who is David Grigory, or what castle are we talking about in this context? And with a question like this, any retrieval model worth its salt is going to basically find the page on David Grigory. It's not trivial because there's, David Grigory the physician, there's the mathematician, there are, I think, actors, and it's a common name apparently. But sure, this one talks about a castle, so a good model will find it. So now we can go back and repeat this process and basically ask the language model, hey, did you learn anything from this? And if you learn something, does that affect what query you would like to search? And the model will say, well, sure, how many floors are in this castle? So we can retrieve and we find this Canardi Castle page, which sort of tells us that it has 5 stories. And so a language model can look at both of these and say hey, Canardi Castle, which this guy inherited, has 5 stories, which is correct. So that was a bit of a mouthful there. But hey, this sort of helps with our extremely simple question, but it took this many steps to sort of get these very powerful language models and retrieval models to solve it. And this is something that we'll see over and over and over again in harder and more challenging tasks. So many years ago, like 3 years or 4 years ago, I built this Baleen system, which sort of was operating in a much harder world where you couldn't prompt language models to do stuff that was hard, you had to fine-tune them. And so it was sort of showing that if you just do multi-hop retrieval, it's actually not that great, and you can actually sort of iterate on the pieces and optimize them so that you push it to be much better. Baleen is not what we're trying to talk about today. But what we are trying to talk about today is this notion of language programs. So these programs that are operating not just on integers or strings or networks or graphs, but also in natural language. And they are programs in the true sense of the word. They're actual control flow running on your CPU in a well-defined sense. But now we have these well-scoped pieces, these modules, that operate on natural language as a first-class construct. And we're going to see that this will affect the way we program stuff, not just in the sense that you are going to send a string to a language model, but in much more interesting ways. So what's cool about these types of language programs, and I kind of spent basically all of my PhD building various ones for various tasks, is that they can actually be really cool in terms of quality. You'll nail tasks you can't nail otherwise with them. And they're really efficient, as I said, and they're quite transparent. The problem, though, is, basically, it's very hard to build them. So you need a lot of research, you need many months, and maybe somebody with experience in this stuff, and you need a lot of annotated data, for your task, or really advanced algorithms to sort of figure out how to train the components of your system. And this is an important part. You're training a system where there's like 5 language model calls or 10 language model calls. How do you actually teach the model to do each of these steps was hard and remains hard, but in different ways. So one of the big questions I think about all the time is, these language programs are awesome. How can we make it easier to build them without these two problems, right? Without this sort of research and all that stuff. So let me know if this is kind of overall clear, and we'll jump right into DSPy now, given this context. Awesome, thank you all. So these language programs, fast forward to today, are advancing many tasks. They look different, and they're more interesting, I'd say, in some ways, thanks largely to the fact that we can actually adapt models to tasks in natural language. They always processed natural language, but now we can actually instruct them in English. And this is not news to anyone here, obviously. But what's really cool is that now we can build systems. This is a system that we built at Stanford, sort of extending the line of reasoning in Baleen. But this is not answering these simple questions that we looked at before. It's actually generating entire Wikipedia articles for new topics with an outline, with citations, and with very interesting sort of ability to synthesize new information. And you can see here that all of these moving pieces involve language model calls or retrieval model calls in a much more sort of sophisticated pipeline than we saw in the multi-hop example. And this is built in DSPy. This is another system we built at Stanford in DSPy, which is trying to do a really interesting thing that I thought was not possible. So this system here is built by Yeji Ashao at Stanford, and this one by Carl as the lead authors. So Carl sort of approached me here and said, what if we show that you could do with in-context learning, with language models, classification tasks where you're given 50 labels, just 50 labels, and your label space has 10,000 labels. So you're given a document, and you're supposed to figure out which of 10,000 different labels fits. And you're just given 50 labels in total as sort of data that you can leverage. And it turns out that you can actually build a language program and optimize it in DSPy to get really high accuracy for this stuff. And I think we'll briefly mention that near the end with some numbers. So this stuff is not limited to 1 or 2 tasks. The literature is rapidly applying these types of language programs to all types of stuff, these pipelines. So this is a DynSQL, very, very cool work for text-to-SQL. This is RAR from Google, very cool stuff for revising language model generations and adding citations post hoc. It's kind of like the opposite of RAG. You generate and then you retrieve here. And this is a very cool sort of work called Alpha Codium that sort of has an interesting pipeline for generating code. And what's really common to all of these guys is that they are really exciting for me and really exciting for anyone who wants to think about sort of building these types of AI systems, because they're really modular. Each of these boxes is playing an interesting role that you can sort of take out and plug into a different system, and you can have a really nice sort of software engineering way of thinking about this, where you're maintaining these systems, you're controlling them, you're scaling them much nicer than an opaque model would allow you to do. It's a very interesting way to operate. The problem is that in practice, all of this is dependent on these language models, which are very sensitive to how you actually prompt them under the hood. And so in practice, you have these amazing diagrams that are sort of really modular, but in papers and in code sort of repos and elsewhere, and I'm obviously very guilty of this myself in many cases, you actually find that these systems rely on these massive prompts that are very kind of carefully tailored for a particular model, for a particular subtask, within a particular domain. And you see this for all types of stuff. And so we're building these really modular systems, and sort of the sky is the limit, but at the end of the day, we're writing tens of kilobytes of JSON strings. And that's the core of our systems. And on one hand, if you are a software engineer or an ML engineer or whatever it is really, this is deeply dissatisfying from it's really inelegant, let's say. I used to do Ruby long time ago, it's really inelegant. But much more importantly, this is extremely messy and ad hoc in ways that will really affect things you care about. And so in practice, for example, people approach us all the time and they say, hey, we like that paper those folks released. It's very exciting. The results are great. It makes a lot of sense. But they kind of wrote their prompts assuming that particular benchmark or that particular data set. We have a slightly different setting. We'd like to leverage their insights. We have no clue in the world how they decided to write their prompts like that, because it's not part of the system. It's kind of like a hidden sort of element beneath. We don't know how to write prompts that look like that work as well for our task, and so this thing is basically a lot less useful than it can be, right? So for you guys or for other people building those things or sort of adapting those things, you're given this thing that's like a cool demo, can't really use it productively. So the kind of motivation behind a lot of the stuff in DSPy is like, can we do systematic machine learning, but for these types of language programs? And this is kind of an interesting point, because we are back to machine learning, except that it's a much higher level of abstraction than it ever was, and it's a lot more accessible than it ever was. But you still need to sort of be principled in how you go about solving problems. If you know any machine learning, and you can ignore this if you don't, essentially, in one of the most important things of a particular machine learning paradigm is, well, what is the class of objects, of functions that we're trying to optimize over? Linear models, decision trees, deep neural networks. These ring a bell. These are sort of hypothesis classes is what they're called. So this is a new hypothesis class. It's not a neural network. It's actually a system that has many neural networks, which are language models. And it sort of is really interesting because, unlike the others, we can optimize it in completely different ways, and maybe that's a positive way to look at it. The other way that's less positive is like, we don't know how to optimize them from a research standpoint. You cannot just say do gradient descent through your language program. It's not really that simple. So this is DSPy, which aims to tackle this question through programming and not prompting language models. And the way we're going to do this is at a very high level, so that the two-slide summary is, you're not going to be tweaking brittle prompts that look like this, which at the end of the day, after all this work, language model changes slightly or whatever it is, they don't actually work that well. Instead, unless you work super hard to get them to fit a particular pipeline for a particular model, and then you're out of luck the moment they change the version of the model. So instead, you're going to write a language program in Python. This is actual Python code, and you will let the program itself learn how to use the language model in a way that sort of simulates the steps that you draw in a diagram. And we're going to see a lot of examples of this. So this is now a program, and when you have a program and you want to run it on a device, the device, by the way, here is the language model, you compile for that device. And so the sort of executable thing that you get will be different for different devices, but the compiler is the same. And this is sort of just an analogy that you will find extends here as we go. So this simple program here, with the same model we saw on the last slide, is doing a whole lot better. But the interesting thing is the same program with a much smaller open model still actually beats the long prompt we had in the last slide, and with a much smaller model that you actually cannot prompt, and so you have to fine tune. The very same program, without changes, can be compiled into things that are still, I think, as effective, or maybe slightly more effective, in fact, more effective than this sort of prompt that I took from the literature. So this is, someone who's an expert actually worked very hard to write that prompt, presumably motivated to get the highest score possible. So what makes all this stuff possible is two things. Two big ideas. The first is we are separating the program logic, that code that we looked at, from how we are going to teach the language model to play that role. And so if you look back at this is just code. There are no I'm not writing prompts in a different file and sort of expecting this to look them up. DSPy doesn't have specialized prompts for this task. This is the program. And we've sort of isolated the concern of coming up with these prompts from the concern of thinking about the control flow. I'll explain the code in detail. You don't actually need to read the code. The second thing is, well, we need to figure out sort of on the back end of this stuff, on the algorithm side, how do we actually optimize a language program? How do we optimize how the language model is prompted or fine-tuned for this stuff? And, well, an insight here is that we'll do a lot of nice discrete search over sort of language pieces. But, that's something we'll discuss shortly. So we are working with natural language modules. And so this is the multi-hop pipeline we saw earlier. If you know neural networks, you don't need to, but if you know neural networks, it looks like a neural network. But now we have these layers, which are actually language model calls. So there's a whole neural network actually stuck in here. And we're not passing tensors between these layers. We're actually passing objects that include language, include strings. And if we move this to the side here, the question is how do we allow people to express this pipeline such that we can actually sort of figure out ways to map it to prompts and to map it to modeled weights in effective ways that solve tasks. So this is the code, and let's actually look at it more closely. It's the same code we had before. If you know PyTorch, this is familiar. If you know Python, I'll explain this. If you don't know either, that's a little more challenging. So this looks like PyTorch. You don't need to know PyTorch, but it's sort of inspired by the way we actually build neural networks, in practice, except that this is not a neural network. So you're writing a class, and you just give it any name you want, and your class is a module, but it's composed of modules, right? That's how modularity works. And so you have two methods. One method is just initialization, and initialization is just going to construct the boxes, right? So the blue boxes are this line, generate query, and the black box here, they're all black boxes in some sense, but is generate answer. And what we are going to do for each of these modules is we'll pick built-in modules in DSPy, which is this chain of thought thing. I'll explain more about that in a minute, and we'll give it a signature. And a signature, I think Connor talked about them, but it's just our way of, let's see if we'll get to that, our way of telling the model what it should be doing, not how to do it. There is a long form way to write those, but in the short form, it's nothing but you're going to take a context, like a bunch, like an object of strings, and a question, and you're supposed to give me a search query. This is the shortest way you can write it. You can definitely add more details or include instructions if you want. Oftentimes, you actually just can get away with doing this and get really good results because of the optimizers. So back to this, there's the forward method, and in the forward method, you're just going to use any code you want. This is Python. You could write loops. You could raise exceptions. You can catch exceptions. You can, do like crazy, in principle concurrency or other things. But basically, make sure you're using these modules in here to conduct the language steps. And so you can basically easily construct this thing as a minor small loop because it has this repeated structure. And you're just going to generate query, you're adding things to the context, etc. So the interesting pieces are really this part. This part is the most interesting thing, which is these built-in modules in DSPy that are going to abstract all these strategies that get proposed all the time in the NLP world. And so if you're familiar with chain of thought, this notion of asking language models to think step by step, essentially before they reason, that's a really cool idea. But if you want to apply chain of thought to your system, you can't just say, chain of thought my system. You have to go and actually figure out what's a way to prompt your language model to think step by step reliably in the context of a particular task. And in practice, that means showing it some examples of doing that for the context of your task. We don't want to do that because that is heavily model and task dependent. So under the hood, inside DSPy, and this is not something you need to worry about, but it's kind of useful for understanding, is going to maintain parameters about the instructions. What should we ask the model to do? Demonstrations, which are basically examples of the inputs and the outputs that worked in the past for other examples. And then basically the weights, if you're doing fine-tuning of the underlying language model. Most users don't. We're investing sort of new research into making it more effective and easier to use. And so I think more people will start picking up that type of thing soon. And there are other sort of nice abstractions to constrain the output of language models, like you can assert that, for example, the generated query, I should have done this before retrieval, but the generated query is under a particular length here in this program. And the idea is that you want the compiler to sort of respect this and map this stuff into prompts that help respect these behaviors. So at this point, this is a cool program, and I think you probably believe me that it describes the pipeline we used to have on the site, but the question is like, what are these keywords supposed to mean? What's a context? What's a query? What's a good answer? What's a chain of thought? How is this stuff supposed to work, and how is it supposed to be defined? And let's say that we are the compiler. Let's say that we're actually trying to sort of map this stuff into something we can execute. So we're kind of writing the assembly for this program, which is in this case in natural language for a model. So if you sort of bring in your best sort of prompt engineer at your company and you say like, I'm trying to express this behavior, and you tell them like, this is just a function, so it takes a question, and I'm supposed to generate some reasoning, and then give you an answer, and you ask them like, prompt this thing, prompt a model that does this. The first thing they'll say is, what is the language model? Because it depends, right? So if your language model is GPT-4, maybe they'll write something like this. So they'll have kind of, a nice short instruction. The model is smart enough to figure out the rest. You don't want to waste tokens. It's expensive. It's slow. And then they'll just plug in a simple template, and it will probably work because this is a very simple subtask. Sometimes, it will not work right away. If you go to a smaller open model like Llama 2, 13 billion, a good prompt engineer is not, and actually this is mostly, for some reason this is not what most prompt engineers will actually do, but they're not going to bother with the instructions at first. You can do way better with these types of models by showing them examples. But showing them examples here is tedious because you got to show them how to do the reasoning, and nobody's going to give you data for that. You got to have to write it by hand. And so maybe write 8 examples of some reasoning on some questions that you get. And if you ask them that you really want this thing to be fast and cheap, you're trying to scale, and you want this to be a small model that's under 1 billion parameters, you're going to figure out how to synthesize data, and then train a model on that synthesized data that hopefully has good quality. And then the prompt is going to be short because there's no need for a prompt once you fine-tune the model specifically for this thing. And that's exactly the role of DSPy optimizers, is to sort of automate this process, is to take these signatures and to spit out these stuff, which will probably look very different for different tasks or models. Let's make sure so this thing is going to die, and so what I'm going to do is, I'll just put it on the floor. Big screen. Okay, awesome. Well. I guess we can see the next slide. So DSPy offers, how much did we see? Yeah, it offers a lot of built-in optimizers. We're always building more of these, and it's a hard problem in general. It's not a solved problem. But we're basically under the hood trying to maximize a particular function on your data. I don't think we should spend a lot of time on the formula. And I guess one insight, if you're sort of looking for a big picture idea here, is that one of the coolest things we talked about today is language programs, right? And we are going to optimize language programs by building language programs whose job is optimizing these programs. And the way we're going to do this in practice is that we want to generate instructions, as Connor said, and we want to generate examples, which will be really, really important sort of for doing this. Many optimizers in DSPy. Connor described MiPro or MyPro, or we need to sort of standardize a lot of the pronunciations of these things. I don't know. But a lot of sort of the simpler ones are Bootstrap, FewShot, or sort of extensions of it under the hood. And Connor showed some stuff about how MiPro works, and so I actually will not spend time on this unless people would like to see it later. And so I'll basically skip through this, and then we can come back to it if useful. But under the hood, what the paradigm we looked at so far does is that you can now sort of start thinking about evaluation in completely different ways. And I'll show it here on a benchmark first, and then we'll talk about what you as a practitioner who's not playing on a benchmark can sort of do to use this stuff to the maximum extent. So you go out there and you sort of go on Twitter or you go on Archive where papers are released, and people tell you like, oh, GPT-4 gets 80% on this like math benchmark, or GPT 3.5 gets 50%. And every time you hear that, you should say, like, you don't know what you're talking about. And it could be a PhD from somewhere, it could be a professor somewhere. It's like, you don't know what you're talking about. And the reason is, as we've talked about today, all of these scores depend very heavily, not just on the model, like, for example, one of these two guys, but also on the program that's being executed and on what optimizer or what process was used to actually generate the prompts under the hood. And so I have here a simple sort of black box program that just takes questions and gives you answers. And it's just given a standard few-shot prompt, like a standard sort of simple way that people plug in examples to these things. And it's not optimized besides that. And you sort of see that on this particular task, GPT 3.5 is a little bit better than Llama 2 Chat, and it's like, that's where people would generally say, like, all right, awesome, moving on. But, we know that RAG helps and chain of thought does, and so you could have like 3 lines of DSPy that apply RAG and chain of thought, and another line or 2 that run an optimizer on top of this, and you actually start seeing that without any additional stuff, this Llama Chat model, which is just 13 billion parameters, you can run it on your laptop nowadays in a quantized form, is actually beating the GPT 3.5, with a simple few-shot prompt. And if you start applying agents and you take the original sort of simple prompts people wrote, it's not too good. In fact, in some cases, it can be worse than the simple RAG. But you run an optimizer, and this stuff really starts to help. And then we take the multi-hop program that we built specifically for this, and you can see numbers that are way better when you run appropriate optimizers. So this also works sort of for smaller stuff. So under the hood, this is really cool. I'm very excited about this, and it sort of helps teach us that there's more columns to thinking about these problems than just the language model. In fact, the program and the optimizers can matter a lot more than your choice of language model, because you can take this thing that you can run, I don't know, in a fraction of your phone's sort of coprocessor, potentially, and get really good quality that would rival what you thought GPT 3.5 could do. But now, this is an audience that doesn't care that much about benchmarks, and frankly, benchmarks are just good for sort of standardizing comparisons. And so I want to go through big picture stuff that should be very interesting to the folks that we have here. So what really is DSPy is the first question, because this was long, and so I really want sort of to give you a really concrete thing that you can leave, and sort of when you talk to people, this will be more useful when you think to yourself, and then I'll let you figure out how to talk to people and tell them about DSPy. So should you learn DSPy? And I think we're an interesting framework where we have a few sort of special things. We don't actually tell everyone, yes, you should. So this is going to be something we talk about. And it's like, how do you figure out if you should actually bother, right? Not everyone should bother. Many people obviously should, because this is the future. But we'll see how we can sort of draw the line. What can you build with DSPy? That was cool stuff that was RAG, right? Cool, RAG is awesome. And if this was a framework for RAG, there are a lot of frameworks for RAG. So, this is a valuable thing to do. But can you go farther? I'll show you a lot of sort of the stuff that people have done. Because, I haven't done enough of this, but luckily the community has built a lot of really cool stuff. Put it in production, release papers with it, release demos. Connor was talking about some cool stuff here earlier. And how do you build a new system with DSPy at your day job, or that you're hacking something together that doesn't look like a benchmark, right? So what should you do there? And where should you start, and what's next? So what is DSPy? And the reason it's a little bit confusing, it is confusing, I mean, this is actually true, is that it's 4 different things. And it is my fault for using the word to mean all of them. I think I'm trying to slowly kind of disambiguate. So it's a machine learning paradigm. We talked about linear models, neural networks, whatever. Language programs is a new word. It's not in the paper. We just call them DSPy programs. But this is kind of a new paradigm for building machine learning systems. And this is one interpretation of DSPy. But the thing you learn here is not a syntax. It's more of a way of thinking about a class of models. It's a mathematical construct almost. There's also a programming model. So these notions of signatures, modules, optimizers, not as Python code, but as sort of abstractions that this thing proposes so that it actually works. And this is something that people have to learn, but it can feel abstract because it is an abstraction. A set of optimizers, right? So a lot of the claims we make are abstract, and a lot of the claims we make are concrete. There are algorithms that we're doing under the hood. This is really where the research actually goes, especially that we have an abstraction now. And that's people say DSPy helped me boost my quality, sometimes they just mean the particular optimizer in DSPy that I used helped me boost the quality. And then it's a library, right? So I mean, that's really what DSPy should have referred to, just the library, not the other things, but it tends to, it tends to sort of mean all of the above. So when you're trying to learn this, you're learning 4 things, and you don't need to learn all of them in depth. Obviously, if you're using a library, that's the thing you need to learn. And it's actually a simple library in and of itself. It's very minimalistic, but because you sort of have some level of dependence on the other ones, there is a bit of a learning curve. So should you learn DSPy? And the answer is yes, if you are going to be building and if you sort of are convinced that you should operate in the world where you're optimizing these language programs, because you can swap in models in and out. You can sort of add a new module and check out if it helps or doesn't, and sort of remove it again or explore that space where your prompts are actually not the main thing you're thinking about. You're thinking about the program, you're thinking about your evaluations. There is a bit of a learning curve. This stuff is democratizing a lot of machine learning, but one of the key arguments we're making here is you will need a little bit of machine learning. You don't need to sort of be a machine learning PhD or a machine learning engineer in a traditional world, but if you are a DSPy engineer, you think in machine learning terms, and so that takes time to sort of to pick up. And so we're working a lot on sort of material that help teach that, and we need to do way, way, way more. And so this is very early, and I understand that this is something that we need to really spend a lot more time on. And we're thinking about things like, I don't know, course material that's obviously free and whatnot, but like just recorded stuff that could take people sort of through this process. And the answer is no, if you need an off-the-shelf system that just works. So you see RAG and you want to do RAG for your setup, or you see an agent that you think is a good fit for your application, you just want to plug and play. Stuff is not going to help you. It's just giving you the small Lego blocks, and they're very abstract Lego blocks because they're really, really powerful. But if you just want something that works, this is going to slow you down, in fact. If you want to build your own thing, and you want to sort of compose the pieces and sort of be in control of that stuff, you want to do machine learning with this stuff, but it's with natural language, which makes it a lot easier. Then this is the only thing you have as a fit. Now, this leaves a lot of things, because there's a lot of people who are not really clear that they are on A, and they're certainly not convinced that there's anything off the shelf that just works. That's why they're interested. And so for those folks, it's an investment, right? There's a bit of a learning curve, but if you get it right, this is clearly how machine learning is going to look at large in the future, and you're sort of getting a very early exposure, and sort of you actually get to influence a lot of this stuff. People have a lot of, the community is very, very active. So I hope this answers the question of like, why is DSPy harder to learn than X? And it's actually a very correct question. DSPy is harder to learn than other stuff because this is not a library. You're learning a whole new paradigm and a new sort of machine learning type learning curve. What have people built with this? Tons of RAG systems, right? A whole lot of really good stuff. And an example of this that's advanced is the long article generation we talked about with Storm. People are building judges, and I think we should actually spend time talking about this later. So the evaluation, a lot of the time, is not obvious when you're building a system to optimize it. And so a lot of the times, your optimizer is actually relying on a different program that's doing the evaluation. Sounds scary, but the code is like 5 lines, and it's actually very simple. People have tackled a lot of benchmarks, some really cool results. Theory of mind. I don't know if we have the developer or the engineer that built this here, but like some state-of-the-art results on theory of mind benchmarks, big bench and other stuff. People who try to train retrieval models. A lot of different, well, at least a couple of different really cool sort of projects on generating synthetic data and then optimizing that process in DSPy, AI assistants. But let's look at some of them that are maybe more concretely public. So we did this thing, Arnav we have here, and I think we have Shangyin as well, that improves the faithfulness, the lack of hallucination of language models on tasks where they have to generate long output with citations. And if you measure that, you can actually improve this quite a bit. I talked about Carl's work. He improved over a state-of-the-art GPT-4 pipeline with manual prompting by a whooping 9 points, or 9%, I can't remember, by building the pipeline and optimizing it in DSPy. Replit used DSPy for a nice sort of code diff thing. Admittedly, their post is opaque. I can't really tell what I actually did, but they plugged it into their thing that trained this model. Red teaming with DSPy was a really cool thing, and you can actually see that I don't know if you can see it clearly, but it's essentially sort of this 10-layer language program that by itself isn't very good at this task. This task is sort of hacking, I think, a vicuña model. And, optimizing it makes it a whole lot better with some pretty nice numbers. The number here is 44. I'm sure no one else but me can see it. Sorry about that. There was a nice sort of project on offering constructive feedback to second language learners, to English as second language learners from Columbia folks, a lot better than their original manual prompt. My own advisor at Stanford sort of took the best of 12 manual prompts they came up with for a difficult logical puzzle and ran a DSPy optimizer, and it was 23% better than the best of the manual prompts they had written. Obviously, you guys are familiar, but this stuff would not have been possible without all these amazing, nearly 150. The number is actually larger nowadays. This is an old slide, but grateful to all of these amazing folks and others on this stuff. And obviously, I think there's 40 nice, very good kind of like YouTube videos explaining a lot of this stuff. And so I kind of thought going through the code too much is not productive because you could just look at any of these. And it was actually a funny thing where like folks at VMware sort of used DSPy for a nice thing, and it kind of got out in some of the, sort of got some nice media coverage that was interesting. So I think one of the coolest applications, maybe because it's new, but it's also a pretty big deal, was University of Toronto researchers participated in a competition. And there were 15 other research teams. As far as I can tell, everyone else wrote their own prompts. These guys didn't. And these guys that didn't build a nice DSPy pipeline. This is from their paper. Had like a couple of pieces, but they actually built several programs. And they topped all 3 subtasks of this competition where there were other universities and other sort of research groups participating. But that's not the interesting part. Somebody's got to win. What's not guaranteed is that the winner is at 84, where the second is at 64. And all these other guys, are very, very competent people at writing prompts that are motivated to sort of do really well in this system and in this competition. But this team has a secret sauce, which is not secret to any of you all, which is sort of building their own DSPy program. But nicely, they're actually thoughtful enough to give us the quality of their uncompiled pipeline and their compiled pipeline. And you can actually see something interesting, which we see time and time again, which is, their GPT-4 uncompiled, the unoptimized version with their like original sort of handwritten stuff, is actually outperformed every single row by the compiled GPT 3.5. And obviously the factor of cost is so large, the speed difference is so large that you obviously want to be in this column, not in the GPT-4 uncompiled column. But the other interesting thing is, if you really want the quality to be really high, it's like it has this 97% accuracy, which is just a ridiculous number. Comparing with like the baselines they have in these and the other. Well, they're not baselines. They're the other competitors in this thing. Exactly. Well, anyway. So how should you build? So this was a lot of discussion of like what can you build, and there's a whole lot of stuff. A lot of these examples are open source. These guys will release it, but a lot of the others are actually already open source. If you go to the README, like we list all these like boring links. They look the same, but they're actually different things. So how should you build a new system with DSPy? You have your own problem, and it's very strange. We've never heard of it. It's not in the examples. It's just very different and unique and hard. So the first thing is define your task. What are the inputs to the program, and what are the outputs? And you'd be surprised that this is actually not that easy. Prompting has made it such that a lot of the time we just sort of like go to the model and we want it to help us sort of like figure out what our task is. But no, here you actually need to at least have an initial idea of what your task is. So it's a little bit more thinking, but I think it's like any good software engineering role, machine engineering for machine learning as well. It's a good thing to do. Build an initial program. Start simple. Start with one layer, just a chain of thought. It's always a good kind of initial system. Don't overcomplicate this. Don't even put RAG. Don't do anything complicated. Start simple. Get a way to get 20 or 30 input-output examples. You don't need examples for a complex pipeline. Don't collect chains of thought. Don't get really weird prompts. Just find a way to get 20 inputs, 20 questions or 20 documents, whatever it is that your input to the system is. Now, a lot of people will say, like, I don't have the time to get 20 questions. But you actually ask them and you say, like, can you get 4? And they're like, no, I can't get 4. And it's like, do you actually even know what your problem is if you can't get 4 examples? Like at that stage, like, do we even know what you're trying to do? And if you get 4, it's actually easy to get 20 because you could send the demo to your friends and they're like asking questions and then now you have 20, right? So what do they look like? They're not long. You know, they might just be like a question like this and then something about like some signal about what the answer might be, right? So I have, again, I know no one else can read it, but you can trust me that there's English here and they're actually very short. So we said these, come up with an initial metric. We can do a better job telling people how to build metrics, but in practice, you know, we could have a simple program. We have examples where you're like, hey, GPT-4, help me judge this. That's not a great metric in general, but it's definitely a good initial metric. Start with things that suck, and we'll iterate on them. For a lot of these things, string inclusion is pretty powerful, because if you have a golden thing that you think should be there, it's a pretty decent signal. Again, it will initially be, you know, not the best, but we'll iterate. Pick an optimizer. We have some guidance on which optimizer you should pick for different types of problems. We're working on improving sort of our own understanding of what you should apply, but there's only like 5 or 6 there's really 3 or 4 that you might be interested in at any point in time, because like we generally try to improve, and so we deprecate all things. For optimizing, you might actually not want to use these data because you might be using it to validate what you're doing or to just get a sense of stuff. Trust me, your problem is not that unique. Somebody has built data, or you can synthesize data from stuff that looks roughly similar. Yes, requires some creativity, but it's a skill worth learning. Figure out ways to get data for training. The quality doesn't need to be that good. The quality of these guys needs to be good because that's where you'll be hill climbing. But the inputs, DSPy will figure out how to tweak them so that they're useful. This is something we can actually start automating in the future in principle. And so hopefully the demands on this, in our abstraction will be less intense. But it is a step that is worth thinking about. And then iterate. So you go to your program, and you run it on some examples, and you spot the pattern of errors. It's making up facts. Oh, let's add retrieval. It's retrieving things that are not relevant. Let's add multi-hop. Its citations are not accurate. Let's add the assertions. Lots of you get a very concrete way of operating on your program that is not like, I don't know, let's add an all caps and hope the model does something different. You're operating an actual code. So there is a nice kind of article. I don't know if this is far enough or not for like people to actually meaningfully be able to scan it. If it is too far, just let me know and we'll move on. But there's a nice article that's like 8 steps to building your own DSPy, and it basically just expands on each of those, has some links, has like the actual description of which optimizers you should use, and obviously we need to do a lot more of these, but it's a useful article. All right, so how should you start? There's a nice intro notebook. For some reason, it's not really where most people start. I think it might be because some of the docs are not pointing often enough to it. But this is a nice intro notebook. There's like a thing called minimal example, and people see minimal and they jump at it. But it's like the intro notebook is longer, but it's a lot more instructive, a whole lot more instructive. Hands-on tutorial. I think. Oh yeah, this is what I would have done today if today was hands-on. So it's a nice kind of tutorial for a similar type of event that was smaller. And so it actually has some to-do steps. The to-do tells you what to do. It actually has a link to a completed version if you want to like double check. Nicely, everything in it is cached. So if you get the code right, it will actually just run. You don't need an API key, you don't need to set it. If it complains, it means you didn't get the code right. It's kind of a slightly clumsy, but make sure you can actually test it and you have that right thing. It's an interesting way to do a kind of integration test. Yes, this is some codes from there, like bonus stuff, how to do RAG with generation and whatnot. Connor's videos are great. So he has amazing sort of explanation of all this stuff in DSPy, and you don't need to scan this, go to YouTube and write like Connor DSPy. So I'll just end here. What's next for DSPy? And I would have written a slide if I had the time, so let me just tell you off the top of my head. I should know this. So one thing I like to say a lot is DSPy is the PyTorch of language programs. PyTorch is the PyTorch of deep neural networks. And when you look at that, they actually don't try to do too many things. It's a bunch of composable pieces. You have the layers, you have the optimizers. They didn't develop them. They're coming from the deep learning literature, but they have one of the best sort of sets of abstractions and implementations and stuff. And the fact that it's so composable and so clean and so minimalistic, and the fact that you can define by run, you can actually have its forward function. If you don't know what I'm talking about, it's not that important to recognize. But a lot of the insights from PyTorch are things that we are adopting here. And I actually wasn't that obvious. I spent a year and a half thinking broadly in the space, trying all kinds of crazy stuff. And the moment I realized, oh, this could just look like PyTorch, is when DSPy happened. If you're wondering why is it called DSPy, it's because of that. So basically, I did demonstrate search predict, which took me over a year to do. It was the earliest started framework for language models. It was released in December of 2022, so it was not the first release. 19 was released in October. And I was struggling in DSP, demonstrate search predict, because something felt off. And so making this analogy to PyTorch, we just added a Y, DSPy, and then we came up with the backend. But that's why it's called DSPy, was a huge breakthrough in my opinion, because it really made a lot of things click through the analogy with deep neural networks. So this PyTorch thing gives us a lot of guidance in terms of what to prioritize and what not to prioritize. And I can give you more examples, but maybe that's better to discuss, for people who are interested in this. So in the short term, we're doing a refactor. We're doing sort of effort. We're working on efforts to make this stuff more robust. Work with sort of a wider class of models, easier out of the box without more sort of, with a more direct workflow. And a lot of this is really led by Cyrus here and a lot of folks working with him. So Cyrus Maluzi and Kyle and Amir on this part of the team. We're working on new optimizers. It's kind of the research side of things. And so, Arnav we have here, Michael Ryan, Christoph Hong, and Delara, so who at Stanford. These are amazing sort of PhD students and master's students, sort of looking at, what is the future of optimizing for harder tasks with less data, where you're updating the weights efficiently, not just the prompts. And let's see what else. So refactoring, a lot of sort of production type improvements in the workflow, and a lot of better optimizers is some third thing that I really wanted to mention. But if I don't immediately remember, I guess we'll wrap it up here, and I'll make sure to inject it down the line well, I guess just much better documentation and examples in general, which I think the state of this has improved quite a lot recently, but certainly a lot more is needed. And I think form of a course is something that is useful. So I should stop here because I'm starting to sort of essentially rant. Thank you all for coming today.